using small molecule drugs, these tiny chemical compounds can cut off an essential survival mechanism for the cancer cell.
We're here to help patients. We still have way too many patients with cancers, with immune disorders, and many other diseases that really don't have good options. Why is that?
Well, Bill, scientists know that there are hundreds of proteins inside our cells that drive diseases like cancer and autoimmune disorders. But here's the surprising thing. Even though we know about all these targets, today's medicines only reach about 10% of them. Just the tip of the iceberg. This is what drives us at Vividion. We're working to address this group of undrugged proteins, and we're doing so by using small molecule drugs, one of the best established categories of drugs. These tiny chemical compounds can slip into specific parts of a protein and either block it or boost it. But in either case, they will affect further growth of the diseased cells.
Yeah, Bayer is not new in the small molecule business. Aspirin is, I think, 126 years old, one of the real classic small molecules of all time. In recent decades, people have turned to proteins like antibodies. Now even we're working on cell therapies and gene therapies. You're working with small molecules. Explain that.
For one, they're simple to make and distribute. They also tend to be easy to take, usually as an oral pill. And once inside the body, they behave in predictable ways. So the combination of accessibility, convenience, reliability makes them a powerful tool.
I mean, that's great, but if it was that easy, we would have pills for all these diseases. And there's something like 90% of these proteins we say we can't drug. We can't find a small molecule to get to them.
Yeah, I mean, that's with the traditional way of drug medicines, right? The key for a small molecule drug to work is to bind to the disease-causing protein. Small molecules can only bind to certain kind of protein shapes, which is one big reason so many disease targets remain out of reach. So the proteins that traditional drugs have been able to hit are usually the ones that naturally interact with small molecules. And think like hormones, vitamins, metabolites. And these proteins tend to have deep pockets on their surface, where a small molecule drug can easily slip and make a strong connection. But here's the catch, most proteins don't have deep pockets. They're smooth, flat, flexible, and this makes it very hard for a small molecule to grab on. And since most drug design has depended on these deep pockets, a huge swath of disease-causing proteins has been considered undruggable.
So what are you guys doing differently? Like, how do you solve that problem?
The traditional way to make a new medicine is to pick one disease target and invest years and millions of dollars trying to design a drug for it. But if it turns out the protein isn't druggable, you've hit a dead end. At Vividion, we flip that process on its head. Instead of choosing one target upfront, we screen thousands of proteins at once to quickly spot which ones have hidden binding pockets. Then we double down only on the proteins that show real promise. This means we are not limited to the deep pocket proteins of the past. In other words, proteins that were previously off limits are now our fair game.
I love that. And one of the things that I was most excited about when I first heard about Vividion was just that opportunity. From a practical standpoint, what's an example?
Yeah, so a great example is our clinical program aimed at a protein called Werner. So Werner is an enzyme that cancer cells rely on to survive. But for years, it was considered undruggable because it lacked a good pocket for the drug to bind. So using our platform, we identified a new binding site on Werner where a small molecule could attach and lock the protein into an inactive state. By shutting down Werner, we cut off an essential survival mechanism for the cancer cells.
That's really fascinating. What are you seeing about the actual effect on the cancer cells?
Well, the early clinical data we have been encouraging. Our Werner inhibitor is showing signs of activity in patients, and it's just one of our 4 novel experimental medicines we have brought to the clinic. Beyond Werner, we are targeting difficult to treat cancers, for example, squamous non-small cell lung cancer, colorectal cancer, prostate cancer, just to name a few. We're also working on developing new ways to treat immune disorders. These are areas with very few effective treatment options today.
But when can we imagine one of these medicines actually making it to the market to help maybe thousands or even millions of patients around the world?
On average, it can take 10 to 15 years from the very first discovery in the lab to the point where patients can actually receive the treatment. That said, we could have potentially a drug to patients by the end of this decade.
Wow, Alex, that's really exciting. End of this decade, possibly. We're going to be rooting you on. Thanks for all you're doing for the mission.
Thanks, Bill, and thanks for all the support for Team Bayer.